All right, so today what we're going to be looking at is compound inequalities. So we have to define first off what compound inequalities are. We're going to write and solve compound inequalities. The nice thing about this is that it's actually nothing new, except just more of what we've already done. So by way of warm-up, let's take a look at here. Hannah has some blue paint, and she wants to lighten the shade, so she mixes one cup. So if you look in there, 1 cup is still too dark of white paint at a time. And after adding 4 cups, she decides that the color is too light. So up here it's too dark, down here it's too light. Explain in words how much paint Hannah should have initially added to get the shade that she wanted. Good, so in words it comes up something like this. She should have added more than 1 cup, but less than 4 cups of white. Does that mean the answer should have been 2 or 3? No, because you could add part of cups. So it doesn't have to be she did it just 1 cup at a time, but you could go 1.5 cups, 1 2/3 cup, 2.5 cups, etc., or go by fourths or something like that. Now, part B. Represent your answer to part A with one or more inequalities. So here we had a single inequality that's extended, and we see that X being the number of cups that she should add of white paint, should be less than 4 but greater than 1. Somebody could have said something like this. You could have said, well, X has to be greater than, actually, let's be more specific, greater than 1. I am going to delete that down there because I don't think it was correct. So X is greater than 1 and X is less than 4. Or some of you might have said, instead of the word and, maybe you said but. It's greater than 1, but it's got to be also less than 4 there. This is essentially what we're working through today and tomorrow, is when we have more than one scenario, we have a lower bound, we have an upper bound, or we have a split situation. So let's look at some examples of how to write compound inequalities and practice it. So our instructions here. We're going to write a compound inequality that represents each situation. We're going to graph the solution we came up with. So at a bookstore or a library book sale or something, all the books were priced between $3.50 and $6 inclusive. First thing we need to know about this word inclusive is that it means those numbers are included, the $3.50 and the $6. So it could be $3.51. It could be $5.99, but it could also be everything in between. So $3.50 less than or equal to, I'll say B for book price, but you could have said P for price or C for cost, less than or equal to 6. And I don't need a decimal on this one if we're just going pure math. So how do we graph this? That's the nice thing. Graphing is the same as we did before with the open and closed points and shading. And I'm also just going to focus on a few things here. I don't need to have every number under the sun. I just need to have where my numbers live. So the first one is $3.50, closed point there. The highest is $6, closed point there. And what we do is connect the dots here. So we're saying the book prices live all inside this range here. It could be $4, $4.01, $4.52, or anything inside there. Out here is not the situation. All right, so as we look at this one, a tropical storm has a wind speed of at least, so notice the term at least has to include 40. But no more, and there's, my apologies for that, should be no more with no T, but no more than, or not more, I guess both work, 74 miles per hour, and M here being the miles per hour. You could have said T for tropical storm, you could have said S for speed, V for velocity, something else like that. All right, so good. We have a lower bound and an upper bound here. So in this situation, another way to have written it is this. I could have said M is greater than or equal to 40 and M is less than or equal to 74. So we could write it as a single extended inequality, or we could write it as two separate inequalities here. There are benefits for doing it either one. There's not one better than the other in terms of correctness. Next, let's look at a different situation, which is similar to the Canby Lake explanation that I gave earlier. So at a local amusement park, if a patron is younger than 12 or older than 50, then he or she will pay a discount rate. Notice that a person cannot be under the age of 12 and also be over the age of 55. That's a logical impossibility. A person cannot be both of those simultaneously. So here's how we write that. So if a patron, and I'll say P for patron, you could say A for age, is less than, notice it says younger than 12. It doesn't say including 12. It doesn't say 12 or younger. It says younger than 12. Here's the big word, or older than 55. So if that patron is older than 55, then they pay a discount rate. So this is how we represent it mathematically. People under 12, people over 55. So all real numbers less than 4, numbers less than 4, or greater than 11, so 11 is less than n. You could also have flipped that around and said n is greater than 11. Again, we don't write it this way because it's sort of misleading, almost seeming that n is between these two numbers when it's not necessarily. Up here, I forgot to graph B. So let's take a moment to graph B here. Remember, when we're graphing it, we don't need every single mark, your scale. In fact, just a few things, a 12 and a 55. If you want to throw another number in there, like a 30 or a 20, that's fine, but this is enough. Now, it's open point because it does not include the age 12, less than, and open point at 50, because it doesn't include, according to the way it's written, it doesn't include 55. It might in real life, but the way this is written, we write this. All right, the next thing we want to do is to go backwards. You're given the graph. We want to write the inequality that is describing it. So how can we use an inequality to describe the set of numbers? So before we attack it, notice the shape of the graph. Now, this isn't always exactly, but notice the shape of the graph. In part A above, the graph came together, okay? So if we were to summarize, we might show that the shape of a graph, if you had the word and, or even the word but, we might have coming together like so. If you use the word or, then we might have a split like this. So this is a good general description, Not always, but that's a good general description. We will see an or situation where that's not quite a split like this. But most of the time, and or buts will be combined like this together because there's a lower limit and an upper limit. And the ors are going to be a split. Oh, it's this thing over here or this thing over here. We see a split. All right, so with that in mind, with this brief summary right here about and but being combined and the ors generally being a split, down here we have. So let's see what this part is. This part here is described as my variable, and I can use any variable I want, x, n, t, or whatever, so I'll use n. N here is less than or equal to, because of the closed point, a -3. This part right here is open and goes larger. So we here see that n is greater than 2, not equal to. Because of the split, we're going to say or. Let's go over here and look at this one. Here we see that they come together. So we have an and situation, but we can also combine it as a single. So I'll use the word and for now, but we'll also show you it can be written separately. We see that my variable, I'll use a different variable just to mix it up. B is greater than or equal to a -4. So it's closed. Right here it's closed, and then it is shaded to the right. However, this part is open and shaded to the left. So this part would be b is less than a 1. So if you wanted to combine that as a single, this, by the way, is an answer. You're done. You don't have to go further. This is a legitimate answer. A second way to write it is like this, with the lower limit, -4, and then the upper limit, 1. Notice that only one of them has the equal to part, the one with the closed. So either one of these are acceptable. People like this because it's a lot cleaner looking. People like this sometimes because conceptually we can see the two things going on. All right, your turn. Please do the try-its, 1 and 2. Go. Now, we're going to get into the wonderful world of solving them, okay? By the end of the lesson, we will also look at practical applications, but for now, we're going to solve just raw skills. We're going to look at some that are 1 or 2 steps, like these ones, and then as we see a little bit later, we're going to get into multi-step, maybe some fractions, and some parentheses or more. So we're going to start fairly simple. So let's look at the instructions. We're going to solve the compound inequality, but then we're going to do 2 other things. We're going to graph and we're going to check. Notice that the instructions when you are practicing won't always say these latter 2. Sometimes it might simply just say graph the inequality. So you do the solving and then jump to the graphing. It might say that you have to check, but even if it doesn't say check, as I said, it is always wise, even if you aren't asked to do a check, because this gives us some assurance. Not 100% all the time, but it gives us a good probability that we're correct. So let's take a gander here. The nice thing about compound inequalities is that essentially the words and or just mean that we treat differently. We just treat them completely separate. So I'm going to solve this guy first. I'm then going to solve this one and then bring together with the word or. All right, so let's do this here. So step by step. The first thing I'm going to do on this one here is subtract 5 from both sides. Subtract 5 from both sides. I'm going to bring down the m greater than a -1. Good. Don't forget that when we are dividing here, we have to do divide or multiply by the -1. And to prevent the alarm bells from going, we switch the inequality symbol right then and there. Now we bring down the final result, which is m is less than +1. I'm going to throw the words or in here to be consistent for the entire time. And as we look at the second component, the only thing needs to be done is divide by 7, right here. Which brings me to the final result for this guy. M is greater than 5. So I'm just going to carry that down. So notice what I have here. This is one answer. It's not 2 answers. It's one solution separated by the word or. Either I'm choosing numbers that are less than m, or I'm choosing, less than 1, or I'm choosing numbers that are greater than 5. So what's the graph of this look like? Well, again, we can go straight forward with our graph. We don't need to have all the numbers listed. I have 1 hanging out down here. I have a 5 hanging out down here, up here. If you want to throw a few extra numbers in there, you may, like a 3 or something. 1, 2, 3. So 3 is somewhere hanging out there. I'm going to open point here and shade below it. I'm going to open point here and shade above it. Now the question is, how do we do a check? How do we do a check? In this, anything over here that I select, I expect a true. Anything inside that I select here, I expect false. And anything over here, I expect true. But again, we only expect true for one of them. And we only expect this to be true for one of them as well. So you don't have to choose any of them. There's no real benefit at choosing any of them. But notice what I expect here. What if I select 3? I would expect 3 to be false here and false here. Whoa. So I'm actually going to do that. I'm going to check m equals 3. So I'm going to do it for both of them. So 5 minus 3 is greater than 4, or 7 times 3 is greater than 35. So let's continue here. Now that I've put those in, I get 2 is greater than 4, which we know is false. We expected that. And then over here, we get 21 is greater than 35, which is false. We expected that. So our check is actually good, even though we got falses, because we expected 3 to work for neither one of them. Let's look at another example, and then you're going to practice down here with the two triads. All right, same idea. But this time, I'm going to go a little bit faster here. So I'm going to add 7 to both sides to get 20. I'm going to divide by 5 to get 4. Notice I'm not showing that, I'm just doing it. Over here, I'm going to subtract 3 from both sides. Subtract 3 from both sides to get 8. And I'm going to divide by a -2, which means I flip the symbol and convert this, to a -4, and convert that to a -2. So now, how does the graph work? Remember with the or, there's a good chance that it's going to be a split, but it doesn't have to be. So let's check here. This one here says that x is going to be less than 4. And then here's a -2, like so. So that means 0 lives somewhere about here. So we're saying that x is less than -2, so it does not include it, all those. And then we're saying that x is less than 4. Dun, dun, dun. Less than 4. But notice both of these are less than. So look at which one of these actually overtakes the other one. The green supersedes here because less than 4 also is less than this, but it includes those. So my final answer is it's not both of these together. This right here is my final answer. X is less than 4, and that's it. So notice that if I do choose a number that's less than 4 and also less than the -2, so for example a -3, if I check it in both of these, I should get true here. So let me show you the breakdown on the graph. Everything over here is going to be true. Everything inside of here is going to be true, but only for one of them. And everything over here is going to be false for both of them. So I'm going to choose something that's going to be true for both of them. I'm going to choose a -3. So x is -3. So I expect true on both of those. -7 less than 13. -4 times -3 plus 3 greater than 11. And fix this mistake here. And just to finish this up, we see that in the end, -22 is less than 13, or 15 is greater than 11. So one or both of these have to be true, and it is true. Both of these are true, which is what we expected over here, both of them to be true. All right, your turn. Please take a moment here to practice. You're going to solve the compound inequality, then you're going to graph, and you're going to check the solution. Notice that, remember up here, the one we committed to is this. This is my answer. X is less than 4, supersedes everything. But when I do choose a number, x is less than 4, it does work for both of these. Now let's look at another type of problem. Notice that this one is a compressed inequality. -12 is less than or equal to 7x plus 9, which is less than 16. So we have a lower bound and an upper bound. So what we're going to do is we're going to show you that this can split into two separate inequalities. But then we're going to do the problem over here where we don't do the split. We're going to see that it actually is going to be the same thing. So let's check this guy here. The first inequality we get is this. -12 is less than or equal to 7x plus 9. The other one, and 7x plus 9, is less than 16. So notice here that this overlaps in the two. Now what we do is treat this exactly like we did above. So I'll go step by step to show you what happens here. -9, I subtract 9 from both sides to get -21, less than or equal to 7x. And divide by 7. Notice I do not need to flip the symbol because dividing by 7 is the same as, it's a positive, so it won't affect. Here is x is greater than or equal to negative 3. I'm going to bring the word and down for each level. And over here, notice I'm subtracting 9, again, from both sides of this inequality. 7x is less than 7. And lastly, I divide again by 7 to get x is less than 1. So here's one way to write the answer as an and situation. We have a lower limit and we have an upper limit. So when I graph this, I have a negative 3 living here. I have a 1 living here. If you want to toss a 0 in there, you may. It's going to be closed point at the negative 3, but open point at the 1. We connect the dots, which means anything in here will be true, anything out here will be false for both, and false for both there. So when I do a check here, I'm going to check something that's true. So for example, x is 0 because I like 0 a lot. So negative 12 is less than or equal to 7 times 0 plus 9, which is less than 16. Negative 12 less than or equal to 9, which is less than 16. And let's just double check that. This is smaller than this one, which is smaller than this one. Yes, it works. So there we go. Now what I did in this one was take this and split it up into two separate inequalities separated by the word and. Well, it turns out you don't actually have to do that. If you keep it all together, what you do to one side of the inequality, in this case the inside, I'm going to do to the other sides, in this case the outsides. So if I'm looking at this k and I want to get it by itself, I need to do two things. Number one, I need to get rid of the divide by 4. Then number 2, I need to get rid of the add 11. So I'm going to do this shorthand here, but if on the inside I multiply by 4 in order for the 4's to reduce there, I have to do the same to the outsides as well. Whatever I do to the inside, I do to the outsides as well. So on the left side here, I get 12. The symbol stays the same because I multiplied by a positive. And now just the numerator comes down, 11 plus k, less than or equal to negative 12. Now let's keep going. Just like I did before, whatever I do to the inside, I need to subtract 11. I need to do to the outsides right here. So the left side here reduces to a 1. The k is left on the inside, and greater than or equal to negative 23. So let's just make sure this makes sense here. I have less than, k has to be less than the 1, which is like 0 and negatives, but it's got to be greater than the negative 23. Okay, so it does make sense. Now when we graph it, I have a high and a low. The high, though, is 1. The low is negative 23. I'm not going to bother with any extra points in there. For this one, it's a closed point, and for this one, it's an open point. Connect the dots. To break down the true-falseness, false out here, true here, false here. So let's finish that up with a check. I'm going to choose a nice number, and notice that 0 is a nice number. So does negative 11. Why is negative 11 nice? Because negative 11 here actually kills this. So I'm actually going to choose, with my check, I'm going to choose k is equal to negative 11. Again, you'll see in a second why. So 11 plus negative 11, all divided by 4, less than or equal to negative 3. 3 less than 0 less than negative 3. And there we go. We do see that 0 is between these two numbers. So we got the check and we're satisfied. Now it's your turn. Please practice these ones down below. Now let's look at an application here. Enrique plans a diet for his dog, River. River consumes between 510 and 540 calories per day. If River eats 1.5 servings of dog food each day, how many treats can she have? So how many of these can she have? So we know that for this, we have 1.5 servings, which is going to give me a certain calories. Over here, we don't know how many treats. So let's say T for treats here. T for treats. We do also know some things. This is the upper limit, the high, and this is the low. So when setting up this inequality, we know that 510 is going to be on the bottom, 540 is going to be on the top. It says between, so depending on how we interpret that, do we say less than or equal to, or do we say less than? Well, we can just interpret that later, but for now I'll put this. So whatever the amount here, so this is the total number of calories in terms of a formula. So when I take the 1.5, the 1.5, and multiply it by 320, because that's what it says here, that gets me 480 calories plus 15 calories per treat. So that is the piece that goes inside here. Now all we have to do is solve this. So again, let's walk through. This is the lower limit, this is the upper limit, and this is the diet. Already eats this much, and this is the treat component. All right, so now what we're going to do is subtract 480 from both sides, all sides. So from the inside, I have to also subtract from the outsides here. So this one here becomes 30 is less than or equal to 15t, which is less than or equal to 60. Now, divide everything by 15 because there are 15 calories per treat. So to answer this question right here, this green right here represents this. Apart from regular food, so only treats, how many calories must the treats be? So the treats must be between 30 and 60 calories. So when I do finally solve this, I get 2 is less than or equal to t, which is less than or equal to 4. So practically speaking, River can eat between 2 and 4 treats per day. Per day. Now, notice this doesn't have to be a whole because you could take that treat and split it in half. So you could give River 2.5 treats or 3.5 treats or some other ground up number. All right, now it's your turn to work through these two triads right here. Good luck and Godspeed to you.